Okay, hello. My name is Volodymyr, and I'm working at EPAM Systems. Yeah, and here our team is trying to use XEN hypervisor in automotive world. To achieve this, we doing or planning to do many different things. It includes various changes in the hypervisor, like device drivers, hardware emulation, and so on, and also some parts in OptiE, some integration with real hardware. Also, we have our own build system that can build multiple domains at once. And we are doing all this in open source, and we are going to upstream as much as possible. And at the meantime, you can find all our work on our GitHub. Okay, and today I'm going to tell you about one experiment, one POC that I did. I call it native application. So first I will tell you how I see this application. Then I will tell you some use cases and goals that I try to achieve. Then there will be some implementation details, and then I'll share my benchmarking results with you. Okay, so what is a native application? I see this something like a Linux kernel user mode helper. So, you know, for example, when Linux needs to load some binary blob, or it needs some kernel module to be loaded, it calls for application that does it for it. And so I wanted something like that in a hypervisor. So this is a plain application. It has no MMU support. It can't handle interrupts. It uses plain syscalls. It, as any other application, it runs in master logit mode. It even has no main loop. So when there are no need for it, it doesn't run. And so why we need something like that? There are different use cases. For example, on ARM, we have VM system specifications that says that every virtual machine should have virtual UART device. Like PL011. And there is a question where we can put this emulator. Obviously, the idea is to put it into a hypervisor, but actually we don't want the emulator to run in a hypervisor mode. So there should be some other place for this emulator. Something like this is with TE. TE stands for Trusted Execution Environment, and it is like TPM on x86, but it is a software thing. It runs in special secure mode on ARM core. Problem is that we want multiple guests to work with TE, with real TE, not emulated. And so hypervisor needs some way to handle this. Also, there are a number of different TEs available. Some of them are open source, like OptiE or Google Trusty. and some of them are proprietary. And again, we can't put code that handles the TE into hypervisor. And another use case is a CF driver. Yesterday, Alexander have tell you about shared capacitors framework, and apart from framework, there will be drivers for specific devices, like driver for a GPU, driver for some DSP, and so on and so on. This driver is responsible for context switching for hardware, and again, there can be some proprietary drivers which we can share. We can put them into hypervisor. Yeah, and about goals, it is obvious that application should be isolated from hypervisor. So, for example, when emulator crashes, it will not crash whole system. And if there will be some security issues within emulator, it will not compromise hypervisor. Also, I wanted it to be faster than subdomain. And yeah, regarding subdomain, you can ask me about them because they are here and looks like they are capable of doing all these things that I told earlier. But there are some issues with them. One is that I call scheduler overhead. So generic way to use subdomain is when, for example, emulator case, when guest tries to write to some virtual register, hypervisor traps this access, and hypervisor pauses guest vCPU and then asks subdomain to handle this operation. At this time comes a scheduler which decides when to run vCPU of a subdomain, because scheduler does not know that subdomain is handling a request from guest. There are no link between them, and the scheduler might decide to run subdomain later. And then when subdomain finishes its work, scheduler unpauses the CPU of guest, and again we need to wait for a scheduler to run this CPU on a real CPU. Actually, I had a talk with Dario yesterday, and we have found another solution for this problem, and there will be a design session later today where we will discuss this more. But let's get back to application. In application case, there are no scheduler, so it is pretty straightforward. Guest calls hypervisor, hypervisor calls native application, and that's all. Also, I wanted to be it simpler than subdomain, because subdomain have much code that actually not needed, for example, for emulator. So subdomain setups MMU, it setups interrupt handler, probably it have multiple tasks, and all this is not needed if we want only to emulate some device. Yeah. So guys, let's get to implementation. On the ARM platform, the interesting bit in hypervisor control register, this TGE bit makes the processor to handle all exceptions at hypervisor level. So it looks like there are no kernel, and anything like syscall, interrupts, aborts, and so on are handled right in hypervisor. And in this case, the hypervisor acts as a kernel for application. Okay, I wanted to reuse as much code as possible, so I added a new domain type, because with the new domain type I will have address space, I will have vCPU to hold the state of my application, and so on. But interestingly, you need to create 6 constants in different places of hypervisor and tools to create a new domain type. And 3 of them are in a DOM-CTL interface. Yeah, okay. So how this application looks like? There's only one entity point to application, and when hypervisor needs to call application, it just jumps to this function. As you can see, there is a function number parameter. For example, it can be please handle read, or please handle write, or please do any other operation. And the additional parameters in the structure. And there you can see simple hello world application. It just prints message to a log and then exits back to XEN. Yeah, so I decided not to use hypercalls, but instead added a number of syscalls. Actually, there are only 2 of them right now. One is to exit back to hypervisor, and another to write some messages to log. So how do I switch to application and back? To do this, I need to pause current vCPU that caused the trouble. Then I configure MMU to create address space for my application. Then I use vCPU structure to set saved program counter to point at entry point of application. I enable TGE bit. I change processor state to EL0, which is the lowest privileged level. And then I do standard context switch to go into my application. And now CPU running in EL0 state and executes this application. And when it's done, application calls a paper exit syscall, which is trapped by XEN. Handler for this syscall disables TGE bit, configures MMU back to a domain, and pauses vCPU and switches to it. You may notice that there was no virtual jig context switching, because the application does not use interrupts. And it makes the switch faster. Okay, and about testing, I needed some numbers to compare, because I didn't know will it be faster or not. So I created a very simple benchmark, which is not the best one, but at least I can compare something. So I needed something to call and something to be trapped by a hypervisor. So I called handle that, and I chose SMC instruction. This instruction switches CPU into EL3 level, and it can be trapped by a hypervisor. So I created a very simple handler for this instruction, which actually does nothing. I put this handler in different places, so then I can compare performance I handled this instruction right in hypervisor trap handler. Then I use the application to handle this. Also, I created a subdomain that handles this instruction. And also, I compared it with bare metal platform without the hypervisor at all. So in hypervisor it was handled very easily. I just advanced PC and that's all. Application is also very simple. I just return back to hypervisor. But I have some problems with subdomains. It appeared that there are no working and stable subdomain on ARM platform. But there was initial porting done by Shenbao. It was very initial, so I had to extend it and make it work. And subdomain acts as a monitor for the MU. That means that when hypervisor traps SMC instruction, it asks Minios to handle it. And handle, again, very simple. I just telling hypervisor that, okay, you can resume execution of a domain. Okay, and handling in firmware without hypervisor also is very simple. I just check in function code, and if I see that this is my benchmark, I just return back to auth. Also, I needed a kernel driver to call this SMC instruction, so I created a very simple one. It adds a new proc entry SMC branch, and when you try to read from this proc entry, it calls SMC instruction 10 million times. And to measure time, I just read from that proc entry and getting some results. And yes, I use the Renesas H3 platform with 4 Cortex A57 cores and 4 gigabytes of RAM. And here is the results. So as you can see, in hypervisor it took 10 seconds to handle all these 10 million calls, which gives us microsecond per call. And I compared other handlers relative to hypervisor. So native application was 6 times slower than handling in hypervisor. Subdomain was 10 times slower. And environmental use case gives us a boost about 7 times, I think. So as you can see, the profit from this application, but I'm afraid that it will be not upstreamed in this state, and probably it will not be upstreamed at all, because we want to try another approach with subdomain. Again, thanks to Dario for pointing me some variants. But probably we will find some use for native applications also. I hear that Stefan is interested in them because of emulator use case. So maybe there will be something interested. And basically that's all. You can find my patches, native application source and Minio source on my GitHub. And please ask questions. if you have one. Yes?
Test.
Could you go back to your results table?
Yeah.
Yeah. So how long do you think a typical emulation thing would take? Like if you were doing a real emulation?
Emulation for example, for some UR device. Yeah.
So for example, if it took 20 milliseconds, then the native app would be 26 milliseconds, and its stub down would be 31 milliseconds, which would be, or sorry, microseconds, which is.
Because there was no real handling in my use cases, so this is how to say smallest time needed to trap something and to handle it.
Sure. Yeah, but I'm saying in a real world situation, you're not going to return right away. You're going to do some work. So if it took 20 microseconds worth of computation to handle the operation, then the numbers here would be like 26 microseconds and 31 microseconds.
Yeah, you just can add computation time to these results, and it will be your value.
So I think in terms of emulation, I think the actual time to emulate something is not the real problem, right? So it might not take so long. So what I see problem is that somehow you need to sync back the result of the emulation into the hypervisor because you might eventually need it there. Or you might do, like for PLO11 emulation, you somehow needed to push it back into the console. And that might eventually, so that's, I was thinking about the ITS simulation, which I'm working on, which is even more, which looks like better fit actually than the PLO11 emulation because it's really cumbersome and may take a long time, but eventually you would need to feed it back into the hypervisor, and that might dwarf the, so I think it's a case-by-case decision to get rid of it.
So anytime you want to add security, you will always have you will always use more time. So it's a call between, do you want to be more secure or do you want to handle fast? So you have to draw a call between them, between security and timing there. I'm a little bit surprised on the number 1 microsecond for the hypervisor. I was wondering, is it just an SMC call that's all trapping in the hypervisor and then doing the SMC directly, or do you do some handling in the hypervisor for that?
You're asking about RTF case?
I mean, not the native app on the stop domain, you say you do just trap the SMC and just do an SMC call. For the hypervisor, what do? You just trap in the hypervisor and do the SMC call?
No, I just returned back to a guest, so I didn't do a real SMC call.
Okay. Two context switches. Okay, so you don't pin the vCPU when you do that.
No.
Okay.
So you mentioned like when you want to get out of the native app, it has to call something like app exit. If it doesn't, like, assume a malicious native app, is that a valid concern? And what happens if it doesn't call app exit? Can it be forced context switched out?
Yes, that can be issue. There are some ways to handle this. For example, there will be some interrupts in any case, so eventually we will get back into hypervisor mode, and then XEN can check some timeout value, and if it sees that application running too long, it just can kill it, and that's all.
Does that answer your question? Anyone else?
So if I recall from past discussions, you actually have done quite detailed measurements, and to figure out what the overhead is due in each case. So I'm asking, do you have a guess of what those additional 5 microseconds are between start domains and native app, and what is it? Because I think you spoke about the geek context switch.
Yes, Geek adds most of these 5 seconds. But I also dropped context save for FPU, and that's all. Yeah, so actually it is Geek.
So I'm wondering, how did you envision if the app itself doesn't do its own MMU stuff? How did you envision setting that up? Like how does it know what address space it has? How does it know how much memory it has or needs or this kind of thing? And what kind of access does it have to the guest memory? Does it simply sort of hand in some information and hands some numbers back, or does it have access to the guest memory, or how does that work?
About the first question, at this moment, okay, what we can do? Actually, we can do something like was done in the Linux, so application can request XEN to map additional memory if it wants to. And the same applies to access to guest pages. You can issue syscall or hypercall and ask hypervisor to map that page of a guest.
Okay, but a bit more like an nmap call than.
Yeah.
Okay.
So just continuing on Stefano's question, you mentioned about geek context switch on FPU. You don't context switch anymore do you context switch the P2M or not, the stage 2?
Yes, I had to context switch P2M because my native application works like any other domain. But I'm going to do another experiment and use stage 1 tables instead of P2M code.
So, yeah, but technically P2M code should not be too, I mean, context switching should be quite fast in general. You will take a hit when you go back to the guests or to the L0 because the context switch will be done there. But otherwise, writing in a register should be fine. I understanding for the geek on the FPU because this is quite long to context switch. On the geek is outside of the processor. But for the P2M, so there's few things to consider is you do the measurement on one platform. We may do measurement on another platform and it may be completely different because the architecture is different. So it might be good at some points whether we choose native app to have the number on different platform, on different architecture, not only ARM architecture, not only Cortex, but maybe Qualcomm's, Cavium, etc., just to have an idea why, if the number will be the same, if it makes sense to do that for everyone.
Yeah, we need to try different platforms, but at this time...
I'm not asking you to do the number, but I'm just saying that maybe we want to have a look of what the others doing to know if it makes sense to do that for the project in the future.
Yeah. I think that okay, we really need more tests, more benchmarking to really see if there is any profit of this.
So one last question for me. Where was the MinUS domain running on the same physical core as the guest vCPU? So how was the scheduling of the thing involved?
No, it was running on a different PCPU. Actually, as I said, this device have 4 PCPUs, and one vCPU was used by DOM0, one PCPU was used by DOM-U, and one was used by MiniOS.
So the MiniOS basically could always run because there was
Yeah,
always
yeah.
a free core.
Yeah, and actually there is a kind of problem with that MiniOS. It never calls VFI instruction, so it actually never stops. It runs constantly.
Okay. Do we have another question? And we have a discussion later, which we're still going to have to schedule, I think. Okay. All right. Thank you.
Okay, thank you.
Looks like we have a break.